Theoretical study of lanthanum titanate and lithium lanthanum titanate solid-state electrolytes. Abstract. In this work, we explored the lithium effects in the electronic and magnetic properties of the lanthanum titanate LTO bulk compounds, as well as when lithium atoms are placed into the lanthanum sites with lithium concentration between 0 and 0.5. The study was made with density functional theory. Results showed that titanium cations change their oxidation state from 3 plus and 4 plus. These changes generally holds associated to the titanium D bands at Fermi level, causing that the T2G states move to the conduction band near the Fermi level. Likewise, the main contribution to electronic states near the Fermi level in the valence bands comes the oxygen p orbitals. Finally, indirect energy band gap's magnitude depends on the lithium concentration in the LTO structure in the greater magnitude linked to the lithium lanthanum titanate LTO electrolytes. Introduction. Safe and life cycles of the lithium-ion batteries determined particularly by the thermodynamic stability and the electrode-electrolyte interface. Typically, the liquid and ionic electrolytes have associated poor thermodynamic chemical stability. The strategy is to incorporate the LiLaTiO perovskite as a solid-state electrolyte, turning the chemical electrode-electrolyte interface more stable. Moreover, LiLaTiO is chemically compatible with different electrolytes. In this context, for this work, we modeled the LiLaTiO bulk system constructed by replacing lanthanum atoms by lithium atoms in a 20 atoms LTO unit cell. Model. A reference computational model was built for the LTO orthorhombic crystalline structure based on experimental data. To model to the bulk LTO crystal, lanthanum atoms were replaced by lithium atoms in the LTO unit cell, and lithium concentrations were varied in the range from x equals 0 to x equals 0.5. So different LTO bulk models were built. Calculation scheme. Electronic properties were studied by means of density calculation in LDA plus U approximation with the CEPCPS functional as implemented in the cascade code. Standard non-conserving zero potential way used with 780 electron volts plane weight cutoff and 443 grins. Results. In figure 2 can be seen that once the LTO perovskite structure holds lithium atoms, the electronic band gaps remain indirect. For x equals 0.25, the electronic band gap decreasing 62% compared to that for the LTO bulk material. For x equals 0.5, the indirect energy band gap increasing by 135, 94, and 106 for layered, columnar, and roxal phases, respectively. Therefore, there are insulation materials. In figure 3 can be seen that titanium atoms in LTO lose electrons in relation to LTO bulk phase. For x equal 0.25, the oxidation state of the titanium having greater or less positive charge with oxidation states 4 plus and 3 plus. The electron loss by titanium 4 plus generally holds at Fermi level and move the T2G titanium states to the conduction band. Modify the electronic correlation. For an E-type antiferromagnetic phase, the T magnetic moment decreases from 0.76 LT bulk materials to 0.11 and 0.69 Bohr magnetons for titanium 4 plus and titanium 3 plus cations, respectively. For x equal 0.5, layered, columnar, and Roxal phases, there are only titanium 4 plus cations. That bonds are less covalent and there is a redistribution of the electronic states. State near Fermi level are mainly oxygen p1s, and that is the T2G states were driven to the conduction band. Besides, these LTO structures do not show magnetic properties. Conclusions. We found that the LTO bulk electrolyte undergoes a change from semiconductor to isolator behavior when Li concentration increasing to 0.5 occupied last sites. The magnetic order of LTO bulk is G-type antiferromagnetic, E-type antiferromagnetic, and non-magnetic for Li concentration X equal 0, 0.25, and 0.5 respectively. Finally, the LLTO layer configuration could be the best electrolyte for lithium batteries application with X equal 0.5. Since it is the insulator materials with the widest band gap, 2.946 electron volts, among all the studied systems and therefore could avoid any lithium battery source circuits. Thank you for watching.